Alrighty, so section 2.3, calculating limits using limit laws. Now, the tricky part about limits so far has been the fact that we just wanted to get close, right? That's like the sticky part here, like the icky part. I don't like that. I don't like just getting close. I don't like just guessing. I don't like just investigating things. I want to know for sure what it's going to be and tell me ways to find that number. Right? My mathematical brain freaks out when I see the word guess or estimate. Ugh, please no. Okay. In section 2.2, we use calculators and graphs to guess the values of limits, but we saw that such methods don't always lead us to the correct answer, and sometimes they might mislead us. In this section, we use the following properties of limits called the limit laws to actually finitely calculate limits. Okay, now, this is here. You write down whatever you want to write down. Everything is PDF'd and put up online if you want to print things out, whatever it may be. I'm never going to ask you, like, tell me what the limit laws are. No, I'm not going to do that because we're going to have a lot of them today. This is all up to you, whether you want to write them down or not. I'm going to talk through each one of these. Okay, so we're defining C to be a constant in all of these. That's what the premise is. C is a constant. And the limit as x approaches a of f of x, and the limit as x approaches a of g of x exists, then, and that's as long as they exist. If the limits don't exist, then things go haywire. Okay, what is this first law saying? Well, the limit of the sum is the sum of the limits. It's kind of like the distributive property of limits. The limit of the sum is the sum of the limits. The limit as x goes to a of f of x plus g of x, quantity f of x plus g of x, is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. I can take the limits separately if they're two different functions. Same thing with subtraction. 1 and 2 go hand in hand because addition and subtraction work the exact same way in terms of these limit laws. I can basically distribute that limit into the f of x plus g of x. So if I have the limit as x goes to a of f of x minus g of x, that is the limit as x goes to a of f of x minus the limit as x goes to a of g of x. 3 is a very important one that we will use a lot later on, is the idea that if you have a constant applied to a function, you can actually remove that constant and set it out front. The limit of a constant times a function is equivalent to the constant times the limit. The limit of a constant times a function is equal to the constant times the limit of the function. I can take that constant and set it out front, and it's not going to change the value. Number 4 down here, okay, the product. Works the exact same way with addition and subtraction. The product of the limits, the product, the limit, I gotta say this correctly. The limit of the products is equal to the product of the limits. The limit of the product is equal to the product of the limits. The limit as x goes to a of f of x times g of x is equal to the limit of f of x times the limit of g of x. And then the same thing is true is also for the quotient of f of x and g of x. The limit as x goes to a of f of x over g of x, well, basically distribute that limit to the top and the bottom. The limit as x goes to a of f of x divided by the limit as x goes to a of g of x, provided that the limit of x going to a of g of x is non-zero. Again, if it's 0, well, then the limit of the full would not exist, right? If I say the limit as x goes to a of g of x actually equals 0, well, then the full limit does not exist. It's the only sticking point for the quotient. So all said and done, with rules 1, 2, 4, and 5, it's just basically like you can distribute the limit to all different operations. Doesn't matter if it's addition, subtraction. It doesn't mean if it's addition, subtraction, multiplication, or division. If you have the limit of the operations of the functions, you can distribute that limit into each of those individual functions and evaluate them separately. And this will be very important for us here once we, figure out the substitution rule, which is in 2 slides. So excited to get there. Again, if you needed any one of these are all up online as well. I still see some people feverishly right now, so I'll pause for a moment. Let's see if I've got any new dad jokes. Did I tell you about how I told my wife to embrace her mistakes? She came and gave me a hug. Did I tell you about the benefits of eating dried grapes? Did I tell you that? Raising awareness. Oh, did you hear about the guy who got his coffee stolen? He got mugged. What do you call a math teacher who farts? A tutor. Okay. You get time length of 3 dad jokes to finish covering. That's my rule. Use the limit laws in the graphs of f and g in figure 1 to evaluate the following limits if they exist. Okay, let's find the limit as x goes to -2 of f of x plus 5 times g of x. All right, now remember that our limit laws say the limit as x goes to -2. You're welcome. So I could separate this like just with the addition, right? But what can I do with that 5? Can't I bring that out in front of just this first limit? Or just the second limit. So I'm going to do that as well. I'm just going to do that on the same step. Okay. So it's the limit of f of x plus 5 times the limit of g of x. All right, what is the limit of f of x as x goes to -2? F -2. Okay, what is the limit? 1. Positive 1, right? So this is 1 plus 5 times, what's the limit as x goes to -2 of g of x? Okay, -2. Oh, there's no open circles, there's no nothing. Okay, -1, right? The function g at -2 is -1. All right, so the full value of the function is 1 minus 5, so -4. All right, so part B here. The limit as x goes to 1 of the product is the limit as x goes to 1 of f of x times the limit as x goes to 1 of g of x. Okay, so what is the limit as x goes to 1 of f? 2. What is the limit as x goes to 1 of g? X goes to 1. What is the limit as x goes to 1 of g? It doesn't exist. So 2 times dne does not exist. Why does the limit as x goes to 1 of g of x not exist? Why does it not exist? Somebody explain it to me. I forget. I blanked out. I've lost my memory. Why does it not exist? Oh, somebody tell me. I'll do like I did back in algebra. Pull popsicle sticks now. I don't have the names on them. Sydney, why? You said no before, so I know you know why. Yes, you do. You said it doesn't exist, you know. What's weird about this? Exactly. They're pointing to two different places on the y values, right? On the right side, it's going to 1, or excuse me, -1. On the left side, it's going to -2. So the limit as g of x goes to 1 from the left is -2. The limit as g of x goes to 1 from the right is -1. So therefore, the limit does not exist. When you see this, and we'll talk about it as a discontinuity, when you see this discontinuity in there, then that means limit does not exist. And if we can say here, if part of this limit does not exist, then the whole limit does not exist. Okay, the limit as x goes to 2 of f of x divided by g of x. Okay, well that is just the limit as x goes to 2 of f divided by the limit as x goes to 2 of g. Okay, so what is the limit as x goes to 2 of f? All right, of f, what can we estimate that to be? Let's say 1.5. Yeah, it might be like 1.4, but let's say 1.5. What is the limit as g goes to 2? 0. Uh-oh. So what is this limit equal to? Nothing. It doesn't exist. This one doesn't exist either. Because I would be dividing by 0. The limit as x goes to 2 of g, well, at 2, g crosses the x-axis. So that means that its value is 0, so therefore the full limit does not exist. See how that works? Okay. Now, this is where we get to some fun stuff. Okay. We're going to start compiling rules and laws to use to really evaluate limits. This is where we can step away from the caveman method, the plug and chug method, to get to something a little bit more refined, a little bit more eloquent. If we use the product law repeatedly with g of x and f of x, we can obtain the following law. This is the power rule. This is the power rule. Or the power law, excuse me. Power law. It says that if you have a power on the function, on the function, you can take the power of the limit. Okay? Basically saying that it's kind of commutative there. I can take the limit of f of x to the nth power, or take the limit of f of x, raise that to the nth power. Now, we can kind of compile all of these as well as two special limits. And this one, my friends, is going to be like the key to unlock solving a lot of limits. But 7 can't be understated either. The limit as x goes to a of any constant. The limit as x goes to a of any constant. Now think about that graphically. If you've got a constant, if you want to graph a constant, just a horizontal line, right? Okay, what if I take x to be 1? What's the value of the function? The constant. What about 2? It's still the constant. What about -1? It's still the constant. So no matter what a value I choose, it's always going to end up being the constant again. The limit of a constant is the constant. The limit of a constant is the constant. Limit of x going to 7 of 3 is 3. Limit of x going to a of 3 is 3. Now, this one is a very important one here. The limit as x going to a of any function x, just limit of x going to a of x, is a. Okay, now that is just, think about the diagonal line y equals x. Think about the diagonal line y equals x. As I make x any value a, so x going to 3. If I say x, want to make it 3, Well, then in the diagonal line, as I get closer and closer to 3, the y value gets closer and closer to 3 as well, right? But that is going to be a very powerful statement when we start applying other rules. Now, these limits are obvious from an intuitive point of view, but the proofs are, and I'm going to say this a lot from here on out. The proofs are all in the book for these rules. Like the author of this book is really good. Like they put the proofs to every single theorem and law that we have like in the back of the book. So if you ever have some time on the weekend and do a little light reading, take a peek. But now we can kind of expand this. Okay, now we can expand this and say, well, if the limit as x goes to a of x is a, like the limit as x goes to 3 of x is 3, well then if I raise that power, if I combine the power law and that 8 above, we can get this. The limit as x goes to a of x to the nth is a to the nth. Okay, well, I mean, that follows, right? I've got the power law, and I've got this rule that says x going to a of x is a. Well, just apply a power to that. So we're saying the limit as x goes to 2 of x to the third power is 2 to the third power. Right? I can just replace that x with a. I can also do the same thing with radicals. I can also do the exact same thing with radicals. Because in essence, aren't radicals just fractional exponents? Right? So they kind of work the same way as exponents. So if I want to take the limit as x goes to a of the nth root of x, well, that's just the nth root of a. Where as long as n is any positive integer. And if we say n is even, like square root, we assume that a is greater than 0, because if we didn't, then the limit would not exist. Because the value would not exist. I don't think 11... Oh, okay. I see what they're saying there. The limit as x goes to a of the nth root of f of x, I can basically apply that limit into the root. This is almost like I could have put this back in like the limit laws with all of the operations, because the radical is kind of like an operation, right? I can take that limit and apply it to the inside of the radical, and that's not going to change anything. Okay. Let's try to evaluate a limit without plugging and chugging then, shall we? Let's do it. Again, those are all online. Those are all PDF in the notes if you need them. Evaluate the following limits and just. We're not going to justify each step. We're not going to be proving anything here. I just want to evaluate these limits using the properties that we had just learned. All right. We know if I've got an operation, if I've got these operations, I can just kind of distribute the limit in, right? That was the limit laws that we learned right at the beginning. The limit as x goes to 5 of, you know what? And I'm going to pull that 2 out right front of x squared. Forgive me for doubling up on that step there. Minus 3 times the limit as x goes to 5 of x, plus the limit as x goes to 5 of 4. See what I did there? All I did was just push the limit into the function, where I took the constants that were the product, the coefficients, and put them as the coefficients of the limit. All right, one of our limit laws says that if we have the limit as x goes to 5 of x squared, well, that's just 5 squared, right? That is this one right here. The limit as x goes to 5 of x squared is just going to be 5 squared. So that is 2 times 5 squared. And we had the limit as x goes to a of x was a. That's straight up that next one. So the limit as x goes to 5 of x is just 5. Okay, what is the limit as x goes to 5 of 4? The limit of a constant is what? The constant. So 4. It's not the a value. Doesn't matter what the a value is, right? Doesn't matter what x is going to. The y value always is the same thing. The limit as x goes to 1,000,000 of 4 is still 4. And so now we can evaluate it.
Ninth graders at this time, ninth graders, last names beginning with F through T, please go to the Performing Arts Foundation for your health screening. That's ninth graders, last names beginning with F through T, please go to the PAW now.
Okay, so this is exciting. Well, for me, I find these things exciting. This is exciting. Why? Because I no longer need to take 4.9, 4.99, 4.999, 4.99, and then go for the other side, 5.01, 5.0001, and so forth. This is replacing all of that heavy lifting where we were just plug in, right? All I need to do is just evaluate it like that. Now, okay, we're going to get here in a second. Can anybody tell me what I did to go from here to here? If I wanted to eliminate that second step, what did I do? What did I do with 5? I just plugged it in, right? I kind of showed this a little bit earlier on the first day that we were learning limits, but I just plugged it in, didn't I? Okay, that's going to be the substitution rule on the next slide. Now, I'm going to assume I didn't know that. Okay, I'm going to assume that I didn't just figure that out. But let's now do part B. So this is saying, okay, push the limit to everything. And I could show this in 2 separate steps where I take just the limit of the top and just the limit of the bottom and then put it all in, but forgive me. I'm going to say the limit as x goes to -2 of x to the third plus 2 times the limit as x goes to -2 of x squared minus the limit as x goes to -2 of positive 1 now because the minus sign take care of the negative. And then we have the limit as x goes to -2 of 5 minus 3 times the limit as x goes to -2 of x. Okay, let's run these values here. Well, this is my power rule. Limit as x goes to a of x to the third is just a to the third. So -2 to the third plus 2 times, same rule, -2 squared, minus what? Minus what? 1, not -2. The why I'm saying this is I've known from past experience, you guys like to say -2. No. I'm not plugging anything in there, right? It's just the constant. The constant is the constant. So it's 1. And then we have the limit as x goes to -2 of 5. Again, same thing. 5 minus 3 times -2. Okay, let's run the numbers. We've got -2 to the third plus 2 times -2 squared minus 1. Oh, -1, that's convenient. -1 divided by 5, that's 5 plus 6. 11. -1/11. -1/11. Even that, though, some of you are looking at that and be like, so we really have to write the limit every single time? Even that is a little bit labor intensive, right? Some of you might be thinking, well, I might as well just do the old plug and chug method. It didn't save us that much work. I got to write out more, right? The other one, I was just plugging things in my calculator. But we know now that we can take a shortcut. We see it here now as well. If I just wanted to go to there, I could just plug that in, right? All I did pushing the limit in was just allowed me to use the rules before just to plug it in. And that is called the direct substitution rule, the direct substitution property. This is awesome. This saves us a ton of time. If f is a polynomial or rational function, now again, notice the caveat there. Polynomial or rational function. If f is a polynomial or rational, and a is in the domain, those are two sticking points there. It has to be polynomial or rational for now. You might learn that we can apply this to other types of functions as well. But if f is a polynomial or a rational function, and a has to be in the domain, and that's again a sticking point for the ones where, especially the rational ones where I can't plug it in, right? The denominator would end up equaling 0, so therefore x was not in the domain, or a was not in the domain. Then the limit as x goes to a of f of x is f of a. Functions with the direct substitution property are called continuous. We're going to talk a lot about continuous functions in section 2.5. Continuity is very, very important with calculus. However, not all limits can be evaluated by direct substitutions. As follows. Okay, can I move on? Anybody tell me that? No. This one should look familiar. This one should look familiar. This is actually one of the very first ones where we applied the plug and chug method. Okay, this is one of those very first ones that we applied the 0.9, 0.99, 0.999, 1.1, 1.01, 1.001. However, if I took this, the limit as x goes to 1 of x squared minus 1 over x minus 1, and just did straight up substitution. Right? That you can't do that right there. I can't do that because I would get a 0 in the denominator. But there's some of you out there thinking, wait. Can't you simplify that down? Can I simplify that original function down? Yeah, let's do it. So that x squared minus 1 over x minus 1, well, isn't that just a difference of squares? Presto changeo. And we've got x plus 1. And we know back from algebra 2, when you cancel out like that, the function is going to act like the reduced one, right? It's going to act like the reduced one, with one exception, that there's a hole at 1. But do I care about holes with limits? No, I don't care what's happening around it. I don't care what's happening at it. I only care about what's happening around it. So this is essentially the same thing. The limit as x goes to 1 of x plus 1. And now we can do direct substitution to get 2. Oh, of course, the board. What time is it? Oh, the board is telling me to stop for the day. Look at that. That's a good stopping point. The homework let me see how much I got left. Ooh. We got a little bit tomorrow. I don't know. Let's kind of play it by ear. If we finish that homework tomorrow, then the homework will be due on Friday. If we don't finish that tomorrow, then it'll be due on Monday. You're going to be like, okay, how do we get Mr. Lambert to stall as much as possible? Yes. You have paper? Yes. I would like to sign by you. Are you leaving somewhere? Are you going somewhere? Yeah, there's a Friday. Where are you going? Roanoke. No.
My name is actually Tom.
Oh, I see. And then that one.
I was Cheryl. Cheryl.
Yes. 229.
Who's that? Which big?
I had no idea that it was coming up to the end of the period. I was on a roll. I could teach it. I could have just. Yeah.
There is no one.
That's nice. Wow.
I literally, I could have just taught. That seemed like 10 minutes to me. Time flies with that.
Oh, yeah.
Do you not care? My voice is back.
Aaron. He said that. He said that to you. Wait. Where? I don't see it.
Have a great day, everybody.
Great. Place where we're going to chat. I figured it out. No. Wow. Somebody called and they're like, we're full. Or was sent.
Well, you can always take it back.
You don't even
Or
know.
Wednesday. It doesn't matter.
You don't even know.
Thank you.
But how do you know what happened? Did you see what Maggie said? The bistro. They took the last reservation. Oh, you can't even eat there.
Morning, Mr. Labbert.
Mr. Swope, how's it going?
Going good. Free day today?
Every day's a free day.
Excuse me.
Which I can, I mean, he does all the work.
Huh? Who told you that?
You did.
Oh yeah, no. Yeah, actually. I told that to Josh Hankins too. He was texting me like, I'm there for you, man. It's okay. It's not Josh.
Why?
Yeah.
She's going to touch masters of physics.
I actually don't want to.
She noticed like the keyboard kind of procrastinated. She saw the keyboard turn to
Stop making that face.
I showed him today.
she just
I think I want to be athletic.
Nap time! What are we gonna do all weekend? It's time. We got stuff to do today.
Yeah, eat some M&Ms.
Nah,
Yeah,
bro.
from work last night.
Uh-huh.
For what?
Should I come in here and argue this stuff?
Like the black outfit.
Dude, I'm like ready.
Black
Oh, it's freaking peppers.
No way you're being like Cleveland fan. You're probably the only one. Exactly. That's why I said you're probably the only one.
Big deal. Everybody's playing today.
Yes, they're.
I thought he was actually gonna like try to play again.
Oh, I'm a white.
I'm sure the Browns.
I would have shaken his hand.
For real.
I'd say some other stuff. Me? He keeps texting me because he wants to tell me.
Last name.
I'm not treating
Get burnt. Just
Yeah, he has nobody. I don't want anybody.
Down for your health screening. Ninth graders, last name.
I would cut Josh
U
Allen.
through T. Please go to the pod now. Thank you.
First touchdown.
I would take Josh
So
Allen.
that's probably like plus 10,000.
That sounds like forever.
Team scored 5 in the 11.
I'm trying to get a
Got the win now.
Oh no, never mind. That's a faucet.
Yeah, he's goofy. Not freaking Brady just lost his best part of the
When is
Season was.
Actually,
Because I have him on the back.
I'll do it after this week because Kirk Cousins plays Detroit, so he's gonna get.
How you doing, everybody?
Just wonderful.
You doing all right?
Just like your
Yeah,
vice
I
chancellor.
hate this sport.
Oh, Jeff, how good is a bees?
I hate this sport.
Yeah, the cat.
Just sell it.
Look at this.
It's just a
Our
dang.
win plus the law presents.
Not